In this video, we're going to talk about cartels or collusion between firms. So if firms are colluding, then we describe that with the word cartel. So we need to think about, is it easy to form a cartel, or is it a challenge? Is it easy to maintain a cartel once it's been formed? And then what policy should we have? What's the role of public policy towards cartels? One of the things that we need to do is we need to now start thinking about repeated games. Let's first talk about the evidence for cartels. So there have been dozens and dozens of cartels that have been prosecuted just in the U.S., but worldwide there's been numerous examples of cartels that have been punished for colluding in a particular market. It happens in airlines, chemical industries, auto parts, vitamins, electronics parts, lots of different markets. And if you were to just Google cartel, you could probably find lots of examples. One of the more interesting examples, I think, is the Archer-Daniels-Midland case, ADM. Archer-Daniels-Midland produced lysine. Actually, they produced a whole bunch of products that go into chemicals that go into lots of other products. So citric acid and lysine is what they were convicted of fixing the price for. And there's a really good podcast called, it's a This American Life podcast called The Fix Is In. And I think it's an interesting, just listening to a podcast about antitrust law and a case where firms got caught colluding, probably I wouldn't even want to listen to most of those. But this one's interesting because of the way it was discovered, because there was a guy that was an ADM employee. He had done some other stuff and had kind of, it appears, tried to cover it up by revealing this Archer-Daniels-Midland price fixing scheme. And so what he did was he served as an informant for the FBI for several years, and he would get recordings and videotapes of these decision makers for Archer-Daniels-Midland and lots of their competitors meeting to fix prices. And it's fascinating. There was a movie called The Informant that was made on this story. There's also an interesting Freakonomics podcast, and the title of the podcast is called "Why Do Your Eyeglasses Cost $1,000?" Turns out that the markup on eyeglasses is enormous, that almost a typical pair of eyeglasses costs less than $50 to make and is marked up hundreds and hundreds of dollars. And it has to do with the fact that there's basically one company that owns the eyeglass industry. And when that happens, we tend to see prices be very high. So we know that cartels are out there, but we also know that it's hard to form a cartel and hard to maintain a cartel. The reason that it's hard to form a cartel is obviously that it's illegal. And you might say, okay, well, lots of things are illegal, but we still observe them. Well, this is a little bit different because it's illegal, but what you have is firms essentially agreeing to some strategy, some plan. But the challenge with it being illegal is that you can't draw up a contract. If it wasn't illegal, then you'd simply draw up a contract between the firms would all sign it, and then if somebody broke that contract, you take them to court, and they would lose. In this case, it's illegal, so you can't draw up a contract. No court would enforce that contract, obviously. And then the probably stronger reason that against cartels is that the agreement itself creates an incentive for each firm to break the agreement. And we'll talk about that. We've already talked about it a little bit in terms of the prisoner's dilemma. So You might ask, well, why would the firms cheat on the agreement? Well, cheating on the agreement is going to allow the firms to make more profit than if they went ahead and abided by the collusive agreement that's been formed. And we can actually talk about that with the models that we've already discussed. So we've talked about the Bertrand model, and we've talked about the Cournot model in particular, that are one-period games. They're single-shot games. In the Bertrand model, what we know is that the two firms could agree to choose the monopoly price and then split the profits that result. But we also know that if one of those firms just undercuts the other firm's price by a little bit, they can all of a sudden steal the market and nearly double their profit. So there's a huge incentive to break the agreement. You can double your profit if you do. And both firms would face that incentive. If we're talking about the Cournot model, the kind of incentive to cheat is a little bit weaker, but it's still there. Think about the Cournot model where we had a demand curve that looked like this, A minus B Q. There's our inverse demand curve. We had a marginal cost that was constant at just C. If you solve for the monopoly quantity, use this to get marginal revenue and set it equal to marginal cost, and then just solve for Q, what you're going to get is that the monopoly quantity is equal to A minus C over 2B. That's the quantity, the total quantity that you would produce in monopoly. And so each firm, let's just say Q1, there's two firms, and Q2, would then each produce half of this, which would be A minus C over 4B. That would be the quantity to produce if we had a collusive agreement where the two firms act like a monopoly and split the market. But here's the other thing that we know. We know that each firm's best response function looks like this. I'm just going to write it in terms of firm I. But firm I's best response function is equal to A minus C over 2B minus QJ over 2. So if we were to take let's suppose firm 1 believes that firm 2 is going to produce this quantity, the quantity that they've agreed to. If we plug this quantity right into there and you do a little bit of algebra, what you're going to get is that QI equals 3A minus C over 8B. In other words, if firm I believes that firm J is actually going to abide by the agreement, then firm I can do better by producing this quantity, which is actually 3/4 of the monopoly quantity, right? Multiply this quantity by 3/4, you'll get that. So firm I is better off by breaking the agreement, producing more than they've agreed to, and what that allows them to do is take some profit, some market share away from the other firm. So each firm does better than producing more than what they've agreed to. Let's just work through a simple numerical example where we look at this. If we just identify some values for A, B, and C, it's quick to calculate what these things are. So let's suppose we have a demand curve that looks like this, 150 minus Q. And let's suppose that marginal cost is equal to 30. So now we know what we've done is we've said, okay, well, A here is 150, and B is just 1, and C is equal to 30. Right? So we can easily plug stuff in. If we want to find the monopoly quantity, we can plug that in, what we're going to get, or you could just remember, you can always figure out that marginal revenue is equal to 150 minus 2Q. You can set marginal revenue equal to marginal cost, so 150 minus 2Q equals 30, and that tells you that 2Q is equal to 120, and Q is equal to 60, right? And if you plug things in for the monopoly quantity, that's what you're going to get. If you take the 60 and plug it back into the demand curve so that we can figure out price, you get that price is equal to 150 minus 60, price is equal to 90. So this is the monopoly, right? That's the monopoly, the way that you would, if there was a single firm, that's what that single firm would do. What that means is, if the firms agree to collude, then each firm produces half of that amount. Each firm produces 30. So that would be our collusive agreement. Charges the monopoly price of 90. So, and charges 90. And then the profit that a firm's going to earn, profit, let's say profit for firm I with monopoly, then where I equals 1 or 2, because we've got two firms here, would be the price minus the cost. It would be 90 minus 30 times the quantity that a single firm is producing, which is 30. So that's 60 times 30, that's $1,800. So that would be monopoly profits for firm I. Each firm produces 30, charges a price of 90, and walks away with a profit of $1,800. Okay? So that would be the collusive agreement. If we were thinking about the Bertrand case, so let's talk about Bertrand. Now remember, Bertrand is where the firms are going to pick price. Okay, so if there's a single firm, that firm could pick the quantity and that would result in this price, or they could pick the price and that would result in this quantity. It doesn't matter, but let's think about it from a Bertrand perspective where they pick the price. So what happens is each firm has agreed to charge 90, but now each firm realizes that what it can do is if it charges less than 90, slightly less than 90, it can steal the entire market. For example, let's suppose one firm decides just to charge 89 instead of 90. So a firm undercuts by $1. So they charge 89. Well, if you plug 89 into the demand curve, that means that the quantity that consumers are going to buy is going to be equal to 61. 150 minus 89 is 61. And then profit for this firm that does the undercutting would be their price, 89 minus, that should be 89, minus their cost, which is 30, times the quantity that they produce, which would be 61, and the profit that they're going to get would be $3,599. That would be the profit that the firm that does the $1 undercutting gets. Now, that's slightly less than the monopoly profit. The monopoly profit was $1,800 per firm, which is $3,600. That's the most profit could possibly be. So they don't quite earn that. They almost are able to capture their profit. But the point is that instead of earning $1,800, they earn almost twice that, practically twice. Okay? So in the Bertrand model, that's your incentive to undercut. You can double your profits. And each firm would face that incentive, right? And that's what drives that price down. If we're talking about, now let's think about the Cournot. With the Cournot model, the temptation to cheat on the agreement is going to be a little bit weaker. We'll see that. Each firm agrees to produce 30. Each firm agrees on 30. But now let's take the point of view of one of the firms. If firm 1 is producing 30, then that means firm 2 would want to produce, we can use their best response function, which is right here, A minus C over 2B minus the quantity for the other firm, which would be 30 over 2. So it believes the other firm's producing 30. This is equal to 150 minus 30 would be 120 over 2 minus 15. You get 45. So if firm 2 believes that firm 1 is producing 30, then its best response is to break the agreement and produce 45, produce more than what they've agreed to. Now, if that's the case, if you had one firm producing 30 and the other firm producing 45, then total quantity would be equal to 75. That's going to drive price down, right? If you plug in 75 here, the price is going to be 150 minus 75. The price would be equal to $75. So it drives price below what they've agreed on, which was the 90. And then if we think about the situation that leaves each firm in, then let's figure out what profit for firm 1 would be. Firm 1 is the firm that's still producing the 30. So the price that they're going to be able to sell at is 75 minus the 30 times the quantity that they're producing, which is the 30. And that profit ends up being $1,350. Now, they were the ones that abided by the agreement, and you can see that the profit that they get is less than what they were supposed to get based on the agreement. And the reason for that, of course, is that the profit for firm 2 now is going to be same price, 75, minus the same quantity, but now this firm has broken the agreement by producing 45, and what they get is $2,025. So by breaking the agreement, they're able to increase their profit to $2,025 instead of the $1,800, and it comes at the expense of firm 1, right? Firm 2 steals some market share, and that drives price down, and firm 1 pays the price. Now, if both firms break the agreement, then that means that they're both going to produce 45. So actually, that's not true. If we solve this, they're not both going to produce 45. If we were to take both of their response functions, set them equal, then we get the Nash outcome, and that's what they're going to produce. They both produce this quantity, with both produce A minus C over 3B. And if you plug that in, you're going to get that the quantity for firm 1 and the quantity for firm 2 is equal to 40. In that case, your total quantity is equal to 80. If you plug that into your demand curve, the price gets driven down to 70. It would be 150 minus 80, which is 70. And then the profit for firm 1 is going to be the price, 70, minus the cost of 30, times the quantity they produce, which is 40. That's equal to 1,600. And the same for firm 2, because they've got the same price, the same cost, and the same quantity. So each of them would earn 1,600. That's our Nash equilibrium. Now, what we can do is we can take a look at what the game matrix looks like for each of these games, and then that hopefully will help you relate what we've just done here to what we've done in some previous videos. So if we think about that Bertrand model, if we were to, let's put it right here. Let's put firm 1 over here. Let's put firm 2 up here. They have two strategies. They can either cooperate or they can defect on the agreement. Same for firm 1. So they can cooperate or they can defect. And this is the Bertrand model, so we can think about the outcomes there. If they both cooperate, they're splitting the monopoly profits, so they get the $1,800 in profit each. But if, let's say firm 1 cooperates, but firm 2 defects, that means firm 2 undercuts firm 1's price by a little bit, steals the entire market, so their profit nearly doubles. We're just going to say $3,600. I realize it's going to be a little less than that, but that's not worth worrying about. And the firm 1 in that case is going to get left with nothing. On the other hand, if it's firm 1 that does the undercutting, they're going to get the $3,600 and firm 2 gets nothing. And if they both defect, remember their profit's driven down. It's going to be very close to zero, practically zero. Textbook calls it epsilon, which epsilon's just what a number that economists and statisticians and mathematicians use for a little tiny number, something really close to zero. We'll call it that. If you want to call it zero, it's not that big of a deal. So that's the Bertrand model. Right, here's Bertrand. Let's think about what it looks like for Cournot. It's a little bit different. And the Nash equilibrium here is this defect-defect combination. With the Cournot model, what we've got is a situation, same setup. We've got cooperate, defect, firm 2, firm 1. If they both cooperate, they get the $1,800 in profit each. If they both break the agreement, they get $1,600, so that's down here. If one of them breaks the agreement and the other one doesn't, that's what we've got here. The one that cooperates ends up with the $1,350, and the one that breaks the agreement and produces more than they agreed gets the $2,025. So the defector gets $2,025, and the other firm would get the $1,350. So there's the game matrix for the Cournot game. The Nash equilibrium in both of these games is to defect. And these are just examples of the prisoner's dilemma. We've talked about that before. Now, this can't be the full story because out in the real world, we actually do observe firms cooperating. We do observe firms colluding with each other and reaching this agreement. So what we have to do is we have to say, okay, well, there has to be more to it than this. And the thing that we need to add to this is the fact that most games are repeated. Okay, they may be repeated a finite number of times or they may be repeated infinitely. So we need to account for what happens in repeated games. So I'm going to clear this off and then we'll take a look at that. Let's think a little bit more about this Cournot game where we've got the Nash equilibrium of defecting. But now let's suppose that the game's going to be repeated many, many times. And suppose firm 1 tells firm 2 this. Firm 1 says, okay, look, I'm going to play cooperatively as long as you do. So as I will cooperate. And if you cooperate, then in the next period, I'm also going to cooperate. And we'll continue that until you break the agreement. And if you break the agreement from that point on, from the next game after that, I will not cooperate ever. So for the rest of time, you will get that worse outcome. You're going to get the 1,600 instead of the 1,800. So firm 2 can think about it this way. Firm 2 says, okay, well, so firm 1's going to cooperate as long as I do, and if I ever break the agreement, then they will refuse to cooperate for the rest of time. So I could defect right now. I could defect and I could get that $2,025 instead of the $1,800. That gives me an extra $225 one time. But then the problem's going to be that if they don't cooperate after that, then now I get the $1,600 every period after that. So I'm going to miss out on, instead of $1,800, I get $1,600. So for all those time periods in the future, I'm going to lose $200 that I could have had if I would have cooperated. So I can take $225 one time, and it costs me $200 every period after that. Now, obviously, whether or not it's going to be better for firm 2 to decide to break the agreement or to cooperate depends on how much they discount the future, right? If they don't care about the future at all, then you defect on the agreement. On the other hand, if more reasonably they probably do care about the future to some extent, in that case you're going to have to say, well, what's the present value of all of those $200 payments I'm not going to get, because that's what it's going to cost me. So they have to think about how much they discount the future. They also have to think about whether or not the threat from firm 1 is credible. Is it the case that firm 1 would, from that point on, never cooperate again? Or might they actually cooperate? So they've got two things they've got to think about. Now, if we're going to write, and we call that a trigger strategy. Essentially, one firm defecting triggers the other firm to refuse to cooperate for the rest of the time that the game is played. If we were to write out in any form pretty much what a repeated game looks like or what the strategies look like, it's going to be complex. But it turns out that it's actually fairly quick to identify the Nash equilibrium. And again, I mentioned just a second ago that we could think about a repeated game as being repeated over a finite number of periods, like say 10 periods or 50 periods, or we could think about it being an infinite game, right? Let's start by thinking about finitely repeated games. Finitely repeated games. So the number of periods is finite and the number of periods is known to both players. Okay, so maybe everybody knows that there are 10 periods or 100 periods. And you might say, well, when would that be reasonable? Well, if you think about, say, two firms that are extracting some natural resource from the ground, maybe it's natural gas or maybe it's oil, and let's suppose there's some fixed quantity of that, then there's going to be an end period, and they might be able to estimate, well, how far off is that? So that's a possibility. Or maybe the firms are operating under a patent. So they're producing a product covered under a patent, and that patent has an expiration date. So they know that they're going to be able to produce and sell this good and have monopoly power until that patent expires. Or it could be that, decisions at a firm are made by teams of people, management teams, and sometimes those management teams change. So maybe the management of a firm, somebody's getting close to retiring, and so you know that person is going to retire here in the next 5 years. Then that could give you a good idea of when the end of the game is. Now, when we start thinking about finitely repeated games, we can learn a lot about just that one-shot game. If the game's played in 1 period because that's just a really finite game. But let's think about a 2-period game where you have a game that's played in the first period and played in the second period. And just to make it simple, let's ignore the discounting for now because that's not going to turn out to matter. Let's think about that trigger strategy. So let's say firm 1, their strategy. So firm 1's strategy that they have stated is that in the first period, they're going to cooperate. And in the second, they're going to cooperate if firm 2 cooperated in the first period. But if firm 2 did not cooperate in the first period, they're going to defect. So cooperate if firm 2 cooperated. Otherwise, defect. So let's suppose that firm 2 cooperated in the first period. And now firm 2 is trying to decide what to do in the second period. Well, there's no third period. So firm 2 knows that there's no threat that firm 1 can make to fail to cooperate at any point after that, right? So firm 1's going to defect. In the second period, there's no reason for them to cooperate because there's no third period. Well, if firm 1 is going to defect in the second period, then firm 2 needs to defect in the second period. Now, what that means is if they're both going to defect in the second period, then now if we go back to that first period, firm 2 is going to say, well, heck, there's no reason to cooperate in the first period, right? Because firm 1's not going to cooperate in the second. So what we get is a situation where the fact that the end is known means that neither of them are going to cooperate in the last period. And the fact that they're not going to cooperate in the last period means that there's no reason to cooperate in the period before that, right? Because the reason to cooperate in the period before that was to establish a reputation for cooperating, but that's useless in the last period because nobody's going to cooperate. So you're not going to cooperate in the last period or the second to last period. And that means if you're not going to cooperate in that second to last period, you're not going to cooperate in the period before that. And so the whole thing essentially unwinds. There's no reason to cooperate in any period if the end is known. We call this the chain store paradox. It's true whether it's a 2-period game or a 100-period game or a 300-period game. If the end is known, then the best that each firm can do in each period is to not cooperate. So here's what we can say. Let's write that out. If the end is known, a finite game is just the same as a one-shot game played repeatedly. With the same Nash equilibrium, which is to defect. There was an economist named Selton, a game theorist. Selton's theorem essentially says that if a game with a unique equilibrium is played finitely many times, its solution is that equilibrium played each and every time. That's essentially what Selton's theorem tells us. It's that. So what that means is if you've got a finite game, then The history doesn't matter. You can't establish a reputation, and the future doesn't matter. Your threats are not credible because everybody knows what's going to happen in the last period, which tells us what's going to happen in the period before that, which tells us what's going to happen in the period before that. So neither history nor future matters in a finite game. So those are not honestly very interesting. What's interesting is if we start thinking about infinitely repeated games. So this is the more likely situation. Firms have an indefinite life. There may be an end, but we don't know when it's going to be. So for all practical purposes, it doesn't really matter if we're talking about an infinite game or an indefinite game. The fact that you don't know the end point is what matters. So the chain store paradox relies on that final period. If we're thinking about an infinitely repeated game, we have to think about how firms value that future stream of profits. And that future stream of profits has infinite duration. So we need to go back and just briefly kind of review something we talked about in an earlier video where we were talking about discounting. So remember that the present value of a payment Z, so you're going to get some payment Z. Let's suppose you're going to get that payment in 1 year. And we want to know, well, what's the present value of that? What's that worth right now? The present value is equal to Z divided by 1 plus R. That's your present value, where R is the discount rate. This term 1 over 1 plus R, we call the discount factor. So a lot of times we write it this way. We let R equal 1 over 1 plus R. We call it the discount factor, and then we can write the present value equals R times Z, where R is that discount factor. If R equals 1, then we're not discounting at all. If R equals 1, then there's no discounting. That means that if you're going to get $100 in a year and R equals 1, then the present value of that $100 is $100. That means $100 now is the same as $100 in 1 year. If R equals 0, if R equals 0, then there's infinite discounting. Right? That's where you don't care about the future at all. If R equals 0, then the present value of a $100 payment in a year, I'm not even thinking about that, right? That's live for today, right? So now let's think about discounting, and let's kind of make this model more interesting by thinking about the probability that the game will continue. Let's let P equal the probability the game continues into the next period. So if it were definitely an infinitely repeated game, then the probability would be 1 that the game continues infinitely. But we can make it indefinite. We can say, okay, well, at the end of each period, there's some probability that the game's going to continue, right? 1 minus P would be the probability that it's going to end after this period. Let's suppose that the firm knows that its profits are going to be pi. So pi profits for each play. Profits in each round or play of the game. That means we're going to think about starting in period 0. And then the probability of reaching period 1 is going to be P. The probability of reaching period 2 is going to be P squared. Right? It's P times the probability that in that period 1. So let's write this out. We'll say start in period 0, the probability that we get to period 1 is going to be P. The probability that we get to period 2, P squared. The probability that we get to period 3, P cubed, and so on. So we can think about the expected profit that a firm's going to earn in, say, period T. To come up with the expected value, you look at what you're going to get, you multiply by the probability that you get there. So what they're going to get is profit in period T, and the probability of getting to period T would be P to the Tth power. So the profit firm expects in period T would be that profit multiplied, let's put the P in front, P to the T power multiplied by pi. Okay, so that's the expected profit. So now we can think about the expected present value of that profit. Now we need to multiply by the discount factor, right? And this was for 1 year. If we square that discount factor, we can make it for multiple years. So let's think about the expected present value of the profit stream. Expected present value of the profit stream. So let's just write out what that looks like, and let's call it V. So the present value, the value of the profit that the firm's going to earn in each of these periods. Well, in the 0 period, we would earn pi, right? That's the profit. It doesn't need to get discounted. The period after that, we would earn the discounted value, present value of the amount that it expects to get in that period, which would be, we're going to discount it with R times P times profit. Plus, after that, it would be R squared, P squared times profit. Plus, and we would continue that out until we get to, say, we could write it for just T, period T, plus R to the T power, probability to the T power, times profit, plus, that's what profit would look like. Okay? Now what we can do is, I'm going to write my period 0 profit, and then each of the rest of these has a RP in it. So I'm going to factor that RP out. When I factor it out, when I pull it out of this one, it's going to leave behind just profit. When I pull it out of this one, it's going to leave RP, one set of them, RP profit. And then when I pull it out of the one after that, it's going to leave it squared, R squared, P squared profit. Now, this right here is just what I have written out there, right? That is the value of profit. So I can do this little trick where I can just rewrite this way. The value of profit is equal to profit in period 0 plus RP times the value of profit. If I solve for the value, do a little bit of algebra, here's what you're going to get. It's very simple algebra, but what you're going to get is equal to profit over 1 minus RP. Now we're going to call this thing rho. And essentially all rho is just a probability adjusted discount factor. So here's the discount factor, and we're adjusting it by multiplying it by the probability that we make it to the next period. Okay? So this is a probability adjusted discount factor. Now it turns out that the infinitely repeated game allows for a whole lot of variations on that trigger strategy that we talked about. And we'll discuss that more here in just a little bit, but let's focus on the simplest trigger strategy, right? And the simplest trigger strategy was that in period 0, we cooperate, and then in period t greater than or equal to 1, what we're going to do is we're going to cooperate if everybody's cooperated in the past. Say already cooperated. In every period before that. And then if not, if anybody has defected, say otherwise switch to the Nash. Otherwise defect. That's the Nash outcome. So now any firm whose rival is playing that strategy faces the following choice. So here's what other firm faces this choice. They can cooperate and get the monopoly profit that they would earn by cooperating. Or defect and get, get that profit, what we called profit D, the defection profit, for one period. And then that Nash profit for all periods after that, for all subsequent periods. What we need to do is we need to think about what the present value of that stuff looks like. So I'm going to clear this off and then we'll come back and take a look at that. Let's write out the present value of the stream of profits if a firm cooperates. So present value of profits from cooperating. We'll call it V and we'll put a C up here. That's the value of profits from cooperating. So you're going to get that monopoly profit, period 0. And then we have our rho times monopoly profit, period 1. Right? Remember, rho here is R times P. Okay, so this is very similar to the statement we had just a second ago, except I'm substituting. It's just right here. Rho equals the discount factor multiplied by probability. Probability adjusted discount factor. Plus rho squared times that monopoly profit. And that would continue, right? Dot, 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 dot. not going to write any more of them out. But what that would end up equaling would be the monopoly profit divided by 1 minus rho. If you've got an infinite stream, that's what your present value looks like. If the firm defects, if the firm defects, what happened there? Then here's what the present value of profits looks like. We'll call it V with a D up there to stand for defection. Then they're going to get that profit, that one-time bigger profit from defecting. But then what they're going to get after that is the Nash. So it's going to be rho times the probable profit from Nash plus rho squared times the profit from the Nash outcome, ... I'm going to do that little trick here so I can write this way. I can leave that thing right where it's at, and then I'm going to factor a rho out plus rho. That's going to leave me profit from Nash plus rho, profit from Nash plus, I'll add another one here, rho squared, profit from Nash, ... So I've just factored a rho out from each one of those. This is the little trick that we did up here. And then this right here is just that, right? So we can do the same thing where I could rewrite it where this in parentheses is VD, and then I could solve for VD. Here's what you're going to get when you do that algebra. It's going to be that defection profit plus rho times the profit from Nash, 1 minus rho. So there's our profit from cooperating, the discounted present value. Here's the discounted present value of the profit from defecting. And we want the condition under which cooperation is most profitable. So when will firms cooperate? Well, that's the same as asking when is the discounted present value of profits from cooperating greater than the discounted present value of profits from defecting. So this will be the condition under which the cartel would be self-sustaining. So if this, we would write out this way. It would be profit, monopoly profit, 1 minus rho. When is that greater than this? The profit from defecting, which looks like that. We're going to solve that for rho. Under what conditions? What does rho need to be? Here's what you're going to get. You're going to get that rho needs to be greater than the difference between defection profits and monopoly profits divided by the difference between defection profits and Nash profits. If that condition is satisfied, if rho is greater than this, then we would expect the cartel to be self-sustaining. We called this, what this is equal to, kind of the critical rho, maybe rho star. Because the defection profits are greater than the monopoly profits, which are greater than the Nash profits, that's the order of magnitude of those, we know that this has to be less than 1. So if you just think logically about the relative size of these, you know that that thing's got to be less than 1. Which means there's an important result of this. There is always a probability adjusted discount factor above which the cartel is self-sustaining. Now we could figure out what rho is in the two examples that we've just gone through, in the Bertrand example and the Cournot example, because we calculated what each of these three things are with each of those. So in Bertrand, here's what we saw. We saw that the profit that you get from defection was equal to 3,600. Remember, it was just slightly less than the 3,600, but we're going to call it that. The monopoly profit was equal to 1,800. That's what they split if they, or that's their each of their share if they agree to cooperate. And then the Nash profit, practically zero. I'm just going to write zero this time. If you plug in those things, what you're going to get is that rho equals 0.5. Just plug those into that. If we think about the Cournot model, then what we've got is that the defection profits, remember, were equal to 2,025. The monopoly profit was equal to 1,800. And the profit from the Nash outcome was 1,600. If you plug those in, what you're going to get is that rho equals 0.529. So here's the general result that we can get. The greater the probability of moving to the next period, the greater P, the more sustainable the cartel is going to be. Okay. So that makes sense, right? Because if there's, the higher the probability that there's a tomorrow, a future, the more likely it is that the firm is going to go ahead and cooperate and continue to get the monopoly profits rather than take that one-time payment now, the defection profits, and then suffer through the low profits, the Nash profits after that. If, on the other hand, they don't care about the future, they're probably going to defect. It's also the case that the lower the interest rate, the more sustainable the profits are going to be. Remember that the lower the interest rate, the higher the present value of those future profits, which makes perfect sense. So there are some challenges with the trigger strategy that we've been thinking about here. One of the challenges, an obvious challenge, is that the world that we live in is uncertain. And so what that means is that it can be challenging for firms to figure out when another firm is defecting. So for the trigger strategy to work, it's crucial that each firm has the ability to detect cheating and to then punish the cheating. One of the things that can make that challenging is that there can be uncertainty, say, in the demand curve that they face. Let's suppose that we had a demand curve that looks like this. Let's suppose that there's uncertainty. Maybe sometimes the demand curve looks like this. We'll call it DL for low demand. And then sometimes the demand curve looks like this. We'll call it DH for high demand. And then maybe, sometimes it looks like this, DM. Maybe it's medium demand. That creates problems, right? Because if the firm, let's suppose the firm has picked some price, some collusive price, we could call it PC, but they don't know in any period what the demand curve is going to be, then what that means is that the quantity demanded by consumers could vary between this amount and this amount. right? And so this is caused not by defection, right? It's caused by variations in the demand curve that the market faces. And so what could appear to be, remember, what it's going to look like if a firm defects is that all of a sudden, let's say you're the cooperator, what that looks like is that all of a sudden the quantity you sell goes down. That's what happens with the Cournot. And so what happens is it's going to look the same here if all of a sudden the demand curve for a particular period is DL and the total quantity demanded in the market by consumers is low. It's going to appear to you as if the other firm is defected, right? All of a sudden it looks like the other firm's selling a lot, which takes some of your market share, and you might engage that trigger strategy when all it was just random variation in the market. And then you've got to live with that, the regret of knowing that you wrongfully accused the other firm of breaking the agreement. That's not really probably what you care about. What you care about is that now you're stuck with those Nash equilibrium profits for every period after that. So that's a possibility. There's uncertainty. It's just hard to know. It's hard to identify when the collusive agreement has broken down sometimes. There are things that you could do about that. You could modify the trigger strategy. So instead of saying that if quantity falls in any period, you could establish a range. So if you know that there's going to be uncertainty in the demand curve, you could establish a range of quantities that's acceptable or a range of prices that are acceptable. Another thing that you could do is you could modify the trigger strategy by saying, well, okay, so if you defect, then we're going to switch to the non-cooperative outcome for a period of time. We're going to punish you for a while, and then we'll switch back. We'll try it again. That would be a modification of the trigger strategy that might work. What this means is that there are a lot of trigger strategies that will maintain the collusive agreement. In fact, there's an infinite number of trigger strategies that would maintain the collusive agreement. There's something that's known as the Folk theorem. Folk theorem. Usually, almost always, theorems or lemmas or laws, they're always named after whoever came up with it, whoever first published it. So you might think that it was an economist or a game theorist named Folk that did it, but it's called the Folk theorem because it's just one of those things that even before it was formally proven, I believe that Friedman proved it, but even before that, everybody kind of knew it was true. So it's part of the folklore of game theory. So we call it the Folk theorem, but here's what the Folk theorem says. I'm not going to write it out. I'm just going to read to you what it says. It says, consider an infinitely repeated game with a set of payoffs that exceed the one-shot Nash payoff for each game. That's the games that we've been talking about, right? There are payoffs that exceed the Nash, right? You can get the defection, the monopoly. There are payoffs other than that Nash equilibrium. Then what the Folk theorem says is, then any set of feasible payoffs that are preferred by all firms to the Nash equilibrium can be subgame perfect equilibria as long as the firms don't discount the future too much. So any set of payoffs that guarantee each firm's going to get at least 1,600 can be shown to be subgame perfect equilibria to the game. Let's think about what that looks like for the Cournot game. Let's think a little bit in a little more detail. If the two firms collude, they split $3,600 and each of them gets the $1,800. Right? If they don't cooperate, they each get $1,600 So any strategy that guarantees that they get anything between 1,600 and 1,800 each can be a subgame perfect equilibrium. We can actually draw a picture of that for the Cournot game. We draw a picture where we look at profits for firm 1 and profits for firm 2. The most profit can be is $3,600 in the market. So I'm going to put a little mark here, 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 and then right about out here. That's $3,600 profit. So if firm 1 was the only firm, they could earn $3,600 profit. Let's do the same thing, a market every 1,000 and then 3,600. If firm 2 was the monopolist, they could earn $3,600. I'm going to connect these right there. Now let's put our Nash equilibrium out here. So that's 1,600 for each of them, which would be roughly right there, 1,600. Now, if you draw a little line out here like that, and another one right here like that, then that point right there is the place where both of them earn the 1,600, right? That would be the Nash equilibrium. 1,800 each would be right out here on that line. But what the Folk theorem says, that any set of strategies that guarantees some combination of profits in that shaded area can be a subgame perfect equilibrium for this particular game. So anything in that little triangle out there. Now remember, the firms can never earn more than a total profit of 3,600. That's not possible because the monopoly profit of 3,600 is the best that any combination of the two firms can get. But anything in that shaded area could be a subgame perfect equilibrium. Let's think about some things that make collusion more likely. So there are a lot of details that we can think about how a market works that have an impact on whether or not firms are able to establish a collusive agreement and then maintain it. One of them would be, of course, the number of firms, kind of the concentration of the market. So if you have a small number of firms, let's say it the other way, the larger the number of firms, the less likely it is that you're going to have a collusive agreement. And the reason is that the larger the number of firms, the smaller each firm's share of profit is going to be. You've got to split the profit across a larger number of firms. And it can be challenging to get multiple players to agree on any strategy. So the returns to collusion decrease as you increase the number of firms because you're dividing profit over more firms. It could have a situation where you have barriers to entry in a market. So if there are barriers to entry, that increases the likelihood of collusion. And you can understand that by thinking about what happens if the barriers to entry are lowered and there are new entrants into the market. Well, if you have a new entrant into the market, maybe that new entrant doesn't join the cartel, right? Maybe they just all of a sudden start producing and selling the good, and now that forces the other firms to compete against it. Or it can be challenging because if they do, let's say, join the cartel, now you've got another firm, you've got another share that needs to be taken out. So all of the firms that are already there are going to have less profits, and that decreases the value of maintaining the collusive agreement. It could be that you have a situation in the market where the firms get infrequent orders. Well, if you get infrequent orders, so not very often does an order get placed. Maybe they're large orders that you fulfill. Well, then it's going to be harder for you to figure out if firms are defecting. That means if a firm does defect, because orders don't come in very quickly, it's harder for the other firms to identify it. And so the defecting firm gets to benefit from their defection for longer. So that can be, the frequency of orders can be a thing that affects whether or not collusive agreements are formed or maintained. It could be market growth. So if you think about it, consider a market that's growing a lot. What that means is that profits in the future are going to be bigger and bigger and bigger. And that increases the opportunity cost of defecting. On the other hand, if the market's shrinking, then those future profits are getting smaller and smaller, and so you don't necessarily care about them as much as you would if the market was increasing. Another thing that can matter is the similarity of the firms. So how similar are the firms to each other in terms of maybe the size of the firm, in terms of what their costs look like? And the key here is that the closer the firms are, the easier it is to come up with some agreement between the firms. If one firm is a lot bigger than the other, then the bigger firm's going to want a bigger share of the profits, and the smaller firm might feel offended at that, or so it can just make it harder to form an agreement. Other issues that sometimes come up and that get discussed when you're talking about collusive agreements is when firms compete in multiple markets. Maybe there are multiple time periods, but it can also matter if there are multiple markets or whether or not the firms are all producing a product that's exactly identical, right? Or maybe the products are a little bit different. Those are all issues that you might discuss if we were taking an even deeper dive into this. Another issue that's important is, are the prices public? So if the prices are public, then it's easy to see when one of your competitors is defecting. On the other hand, if firms enter into pricing agreements with customers and they don't make those prices public, it can be hard to figure out whether or not somebody else is breaking the agreement. One of the ways you can fight that as a firm is by having say a guarantee where you will meet or beat any of your competitors' price. So a lot of times if we just went out and asked just people on the street, do you think that's a good thing when firms give you a guarantee that they will meet the competitor's price? Most customers would say, yeah, that's going to give them an incentive to keep their prices low. But really what that does is it causes each customer essentially to be a tattletale if one of the other firms is breaking the agreement. So it's really a way for each firm to identify if another firm is breaking the collusive agreement, right? Because if a customer comes to you and says, hey, your competitor's offering me this lower price, now that provides you information that can be very useful for figuring out when somebody's breaking an agreement. Obviously, the fact that collusion exists and that cartels are formed and exist out there in the world, we need some antitrust legislation, and we need to think about the effectiveness of that antitrust legislation. Essentially, the authorities have a couple of tools that they can use to try to identify when firms are colluding. One of them we could talk about as the probability of detection. So the antitrust authorities can look harder to try to find when firms are colluding with each other. And if they do look harder, then that increases the probability of detection. So firms have to be more careful, right? We can also think about the fines that are imposed. So once firms are found to have colluded, then the authorities can ask for bigger fines. We could let Q be the probability of detection, and we could let F be the fine that is imposed. Turns out that you can rewrite that statement right there for the probability adjusted discount factor, the statement for rho, building in the probability of detection and the fine that's going to be imposed. And you get a statement that looks like this, that as long as rho is greater than or equal to some critical value, which we'll call P rho star, and that critical value now looks like this, the difference between the defection and monopoly profits divided by 1 minus Q multiplied by the difference between defection profits and Nash profits, plus, I'm going to write my second term right down here, plus Q times F divided by 1 minus Q times the difference between defection profits and Nash profits. So this statement can be modified by building in the probability of detection and the fine that's going to be imposed, and you get a more complex statement. But what's important is that you can see that as Q and F increase, that discount factor, that critical value for the discount factor increases. You can also see that as Q and F go to 0, right, if the probability of detection goes to 0 and or the fine goes to 0, this statement just goes right back to that. I guess the important thing to think about is that antitrust policy really isn't designed to fix collusion after it has happened. It's really designed to deter collusion before it happens. That's why you increase the probability of detection, to try to keep firms from colluding. That's why you increase the fine, to try to make them build that into their decision making and say, okay, well, now it's a more complex problem because we've got to think about the possibility that we have to pay this big fine in the future. So hopefully that gives you an idea of kind of the conditions under which a cartel is self-sustaining. And I'll see you in another video.